In the last class, I taught you many things about the Lagrangian mechanics, constraint and constant motion. Constraint is nothing but it is just a restriction to any orientation of the particle system. Today I will teach you about the generalized coordinates. You have good knowledge about the coordinates. You have learned in higher secondary class that the coordinate system is nothing, it is a system to describe a point or object locating in a space or in a plane or in a line. Okay? Sometimes it requires one axis, that is called 1D, one dimensional axis. This is a one dimensional coordinates. In plan to look at any body or particle, we requires in generally two dimensional coordinates, that is along x axis, along y axis. Again, if we want to look at or specify a object, then we require at least three coordinates, say x axis, y axis and z axis. In space, to look at a particle, it requires at least three axes, that is this three dimensional axis. Similar case is happening in Lagrangian mechanics, that is known as generalized coordinates. And what is generalized coordinates? This is nothing, it is the general coordinates to all. We have Cartesian coordinates, we have polar coordinates, we have spherical coordinates. To mean common to all, a special type of coordinates are required, that is called generalized coordinates. For choosing generalized coordinates, we need some important rules guided by us. Number one, their values determines the configuration of the system. Number two, they may be varied independently of each other without violating the constraint on the system. And number three, there is no uniqueness in the choice of the generalized coordinates. Generally, question arises how to choose a suitable set of generalized coordinates in a given situation. The answer is to be guided by us these three principles. Okay? Any doubt? Whenever we represent a Cartesian coordinates for plane, then we choose coordinates q1 as a x, q2 as y, for this is for plane, and for polar, q1 is equal to r is equal to root over x square plus y square, and q2 is equal to theta tan inverse y by x. These coordinates are chosen as q1 and q2. These two coordinates q1 and q2 are called generalized coordinates. And this is the relation between generalized coordinates and plane coordinates. Polar coordinates r and theta as shown in the expression. For spherical coordinates, we required three independent variables, namely r, theta and phi. And each coordinates r, theta, phi are represented by choosing generalized coordinates as q1 is equal to r, and this is equal to x square y square plus z square. Q is equal to theta is equal to cot inverse z divided by root over x square plus y square. And third generalized coordinates q3 is equal to phi is equal to tan inverse y by z. Okay. These generalized coordinates are of great importance in Lagrangian mechanics. Some physical quantities have to be expressed in terms of generalized coordinates. For example, displacement. Displacement is a vector, and this displacement can be expressed in terms of generalized coordinates as position vector Ri. Ri is a position vector, is a function of generalized coordinates q1, q2, dot dot q3n and t. That means position vector depends upon the q1 coordinates, q2 coordinates and q3n and on time. And displacement is expressed as summation of this del Ri divided by del qj, del qj. Similarly, these generalized coordinates can be obtained from Euler's theorem. X is a function of x1, x2, x3 and dx is equal to this and this. Okay? And now, in terms of Lagrangian equation, we have to choose the generalized coordinates. This is the most important application of generalized coordinates in Lagrangian. Now, question is that what is called Lagrangian? Lagrangian is nothing. It is a function depends on coordinates, velocity coordinates and time. Okay? And from the conception of Lagrangian, we can deduce the Lagrangian equation for conservative system as given by this. And this equation actually deduced from the concept of D'Alembert's principle. D'Alembert's principle also involves partial displacement and partial work done. In terms of partial work done, we can able to find out the expression for the D'Alembert principle. For conservative system, it can be shown that Lagrangian equation of motion for conservative system, this d dt whole bracket dl divided by dl qj minus dl divided by del qj, where L is equal to t minus e. And this is a new function recognized by difference of kinetic energy and potential energy of the system. Okay. Next, in terms of Lagrangian, Lagrange's equation can be deduced in many cases. We have so many cases like simple harmonic motion. For example, referring to this simple harmonic motion, the arrangement simple pendulum, spherical pendulum, okay, linear harmonic oscillator. Also, this can be used in case of reduction of Keplerian problem, at Watt's machine and so on. First of all, let us see how we can deduce Lagrange's equation of motion in case of linear harmonic oscillator. And what is the linear harmonic oscillator? Linear harmonic oscillator is nothing but it is an arrangement when a mass of a body is attached to the spring and placed in a horizontal direction which is frictionless. If somebody pulls it from its mean position and release quickly, it is found that the particle will move to and fro with respect to mean position. The motion is definitely is a simple harmonic motion. What is called simple harmonic motion? Simple harmonic motion is nothing that the acceleration acting on the particle is directly proportional to the displacement from the mean position, and also it acts opposite direction of the displacement. The symbolic representation of linear harmonic oscillator is shown. This is spring, this is the mean position. Suppose a particle is located in three positions. One is at x, another position y, another position x dash, and our generalized coordinates is chosen as q1 for x, q2 for y, and q3 for x dash. Okay? So we can have the Lagrange equation of motion in one dimension as this: d by dt del L divided by del x dot, this is dot, minus del L divided by del x is equal to 0. Here we need one important terms, the Lagrangian. L stands for difference of kinetic energy and potential energy. That is, first of all, we shall calculate what is the kinetic energy of the system. The kinetic energy of the system is given by half of mv square, that is half of m x dot square. Secondly, we shall calculate the potential energy. Potential energy is represented by V, and this can be obtained as a dot product of force and dx. By integrating, we may have the expression for V is equal to half of kx square. Here C is equal to 0. 0 is found, it is the boundary condition of integration. How we can obtain that C is equal to 0? Suppose in the motion of the path, if we chose t is equal to 0, displacement from the mean position will be 0. If we put the value of x is equal to 0, t is equal to 0, then obviously we can find v is equal to nothing, v is equal to c is equal to 0. So putting this value on c, this is equal to 0, this is equal to 0. This is the potential energy. Having these two terms, kinetic energy and potential energy, we have the Lagrangian. We have the Lagrangian as L is equal to t minus v is equal to half of m x dot square minus half of k x square. However, this expression, okay, for conservative system, Lagrange equation for one dimensional as stated earlier. Accordingly, we need del divided by del x dot is equal to m x dot. If we take the derivative, then we get this, and derivative of L with respect to x alone, then this gives minus kx. Okay, this is the value of del L divided by del x dot, del L divided by del x, and putting all this value in the above equation, we see so this is the Lagrangian L, okay. So d divided by dt mx dot minus plus. So this is the equation, okay. So x double dot is equal to minus omega square into x. We replaced k by m is equal to omega square. So from this expression we can conclude that acceleration is directly proportional to the displacement from the mean position, as omega square is constant. Okay, obviously the motion is simple harmonic motion. Okay, as it is a simple harmonic motion, so it must possess its time period. So time period can be evaluated as given omega square is equal to k by m, omega is equal to root over k by m. So what is time period? Time period is nothing but this is omega is equal to twice pi. Omega is equal to how much? Time period is equal to twice pi divided by omega. So omega is equal to how much? Twice pi divided by t. Okay. So from this equation we can able to find out the time period of the harmonic oscillator. This is the desired equation of Lagrange's equation. This is called Lagrange equation of motion for conservative system. Okay, any doubt? And next, we can apply it for isotropic oscillator. That is, in case of 3 dimension. Above we discuss is 1 dimensional case, and this can also be transferred to the 3 dimensional case. So, an isotropic harmonic oscillator is nothing, but it can be considered as a vibrating particle that is acted upon by a force directed always towards or away from the main position, such that the force is nothing, it is a restoring force. There is a force which is driving the motion against the mean position. F is equal to minus k into r. K into r. K is nothing, it is a position vector. Magnitude is r. X, y, z are involving the r. Okay. Next, to find out the Lagrange equation, we need to calculate the potential energy as well as kinetic energy. For 3 dimensional case, kinetic energy is equal to this, and potential energy as earlier we have calculated, the value is half of k r square, and putting the value for Lagrangian L is equal to T minus V, difference of kinetic energy and potential energy, and then as earlier we shall find out the value of del by del x dot is equal to this, del L divided by del y dot is equal to this, del L divided by del z is equal to mz dot. Okay. This is for x axis, this is for y axis, and this is for z axis. Okay. And these values are putting in the conservative Lagrange equation as you see d dt mx dot plus kx is equal to 0. So, desired equation for x axis is this. Similarly, desired equation for y axis is that. Desired equation for z axis is that. It is noted from the expression in 3 equation, if we choose a constant omega square, then it is found omega square is equal to nothing, k by m. Okay. So, in both cases, omega square is equal to k by m. From this expression, we can able to find out the time period, how much, as earlier we deduced. For 3 equation, this time period will be the same. Why it is same? Because it is a 3-dimensional body and it is in motion to and fro. That is why, though it is considered in 3 axes, the time period of the body will be the same. Okay? Any doubt? Lagrange equation for plane polar coordinates also can be deduced like that. Over. Okay? The Cartesian coordinates of particle is related with polar coordinates transformation equation as this: x is equal to r sine of theta cos of phi, y is equal to r sine of theta sine of phi, z is equal to r cos of theta, and so on. Okay? And from this expression, we will say about to Lagrangian. Okay, L is equal to T minus V. Putting all this value, we are able to find out the Lagrange equation of motion for conservative system as follows. This in terms of R, the equation is this. In terms of theta, equation is mr square sin of theta cos of theta phi dot square. In terms of phi, required Lagrange equation of motion is this. Okay. These are the required equation of motion in polar coordinates. In the last slide, we shall discuss about the cyclic coordinate. Okay. Already you have a good idea. I told about this in the last class. Okay. What is cyclic coordinates? You see what is cyclic coordinates. Okay. We have shown that Lagrangian is a function of generalized coordinates, generalized velocities and time. Now, if the Lagrangian of a system does not contain a particular generalized coordinates, then obviously for such a system, del L divided by del Qj is equal to 0. That means L, function L, Lagrangian does not depend upon this coordinate. Okay. So, such type of coordinate is called cyclic. Cyclic coordinates sometimes referred as a ignorable coordinates. Ignorable coordinates. That is, whenever any function is taken under the derivative, then coordinate is not considered. Okay. There are many examples for ignorable coordinates. The function, potential is a function of coordinate only. Potential of a system is a function of coordinate only. If we think it is a function of velocity, then ultimately this derivative of potential with respect to velocity, ultimately it will be 0. So, under that condition, velocity coordinate is a cyclic one for potential function. Okay, any confusion? Thank you very much. Now, this is the session to ask me any question, any confusion, any doubt, please ask me. Anybody?
So what is the basic condition for coordinates to be a cycle?
Yes, basic condition is that when a function, suppose Lagrangian is a function, does not depend upon the coordinate qk or qj, qi, then del L divided by del qj ultimately becomes 0. Under that condition, qj is termed as a cyclic coordinate. Okay. Similarly, already I have told you potential energy, potential of a system function of coordinates only, not on velocity. So, under this condition, if somebody forced that potential is a function of generalized velocities, then ultimately del V divided by del Qz dot becomes 0. So, Qz dot is equal to 0. Okay, clear? Anybody? Next, anybody? Okay. You have asked me very important question. Very easy question. Sit down. What are the basic application of generalized coordinates? Listen, there are a lot of things in Lagrangian mechanics that general coordinates are widely used. For example, displacement. Displacement I have shown in the slide. Displacement can be expressed in terms of generalized coordinates, similarly velocity, similar kinetic energy of a system, similarly momenta, conjugate momenta can be expressed in terms of generalized coordinates, and many more applications are there. Okay? Anybody? Next. Okay. Difference between Lagrangian and Hamiltonian. Very interesting question. There is a distinction between Lagrangian and Hamiltonian. In usual case, Hamiltonian and Lagrangian both are function, but dependent variables are different. In Lagrangian, it is found that it depends upon coordinates, velocity and time. Okay? But in derivation of Hamiltonian, it depends upon coordinates, momentum, not velocity, momentum and time. So, in Lagrangian, where the velocity was taken the place and that place is replaced by the conjugate momentum. And there are many difference in between Lagrangian and Hamiltonian. In the equation, as you have deduced, Lagrangian is nothing, but it is a difference between the kinetic energy and potential energy of the system. Okay. On the other hand, Hamiltonian is nothing equal to a summation of kinetic energy and potential energy. Okay. So, vast difference. So, Hamiltonian is nothing, but it is the total energy of the system, that is the summation of kinetic energy and potential energy. Okay. Any other to ask me? Okay. Thank you. Thank you very much.